So in this example, we're going to define a couple of vectors. Vectors are going to be vector v is the vector 2, 4, -1. So it extends 2 units in the x direction, 4 units in the y direction, and -1 unit in the z direction. Vector w extends 3 units in the x direction, -2 units in the y direction, and 6 units in the z direction. We're going to do a couple of linear combinations and fun stuff with these. So let's start with just a simple vector addition. We'll do v plus w. So we'll take the vector 2, 4, -1, and we will add it to the vector 3, -2, +6. So adding each of these components together, the first component will be 2 plus 3. Second component will be 4 plus -2. And the third component, oops, not plus, comma, third component will be -1 plus 6. Perform those hopefully very simple arithmetic steps. We'll get a 5 and a 2 and a 5. Boy, I hope I know how to do arithmetic. For the second part, let's do a linear combination. Let's do 2v minus 3w. So 2 times the vector 2, 4, -1 minus 3 times the vector 3, -2, 6. Now, according to the order of operations, if you will push Eddie please, wait, how does that go? Please excuse my dope-ass swag. That's right. Multiplication should take place before addition or subtraction, so we're going to take care of the scalar multiplication first. We'll multiply the 2 through. 2 times 2 is 4. 2 times 4 is 8. And 2 times -1 is -2. Now for the second one, you have the option of distributing a -3 and changing to vector addition, or distributing the +3 and leaving it as subtraction. I'm going to distribute the -3 and change it to vector addition. So we'll be adding -9, +6, and -18. Adding the corresponding components together, 4 plus -9 will be -5. 8 plus 6 will be 14. And -2 plus -18 will be -20. Cool. Next up, I'm interested in finding the magnitude of v and a unit vector in direction of v. So first off, for the magnitude of v, we'll apply that distance formula / Pythagorean theorem thing that we were talking about. This will be 2 squared plus 4 squared plus -1 squared. We're squaring each of the components, adding them together, and then taking a square root. That'll give us a square root of 21. The unit vector in the direction of v is going to be vector v divided by the magnitude of v. So we'll be taking the components 2, 4, -1, and dividing them all by the square root of 21. So your vector will be 2 divided by the square root of 21, 4 divided by the square root of 21, and -1 divided by the square root of 21. If you feel like rationalizing those denominators, please feel free to do so. Otherwise, it's no obligation to do so. Then we'll do the same thing for w. We'll find the magnitude and a unit vector in the direction. So magnitude of w and a unit vector in the direction of w. We'll start with the magnitude of w. The components were 3, -2, and 6. So we'll do 3 squared, -2 squared, and 6 squared. We'll be adding all of those together. We get 49. Simplifying that radical as much as possible, we wind up with 7. So the vector that we are looking for will be vector w divided by the magnitude of vector w. So we'll be taking the vector 3, -2, 6, and dividing all 3 of those by 7. So 3/7, -2/7, and 6/7. Finding unit vectors in the direction of a given vector is going to be a very big, important problem later on in the course. Now, last one I want to do is the magnitude of v plus w. And for those who are in linear algebra or have taken linear algebra, this is noting the triangle inequality. We calculated v plus w to be the following vector. It is 5, 2, 5. That was back in part A. You can rewind if you need to retake a look at that. That'll be 5 squared plus 2 squared plus 5 squared for the square root of 54, which when simplified gives us 3 square roots of 6. You'll notice, however, that if you take the magnitude of v and the magnitude of w and add them together, you do not get 3 square roots of 6. So a big important note to make here is that when we say find the magnitude of v plus w, we are not saying find the magnitude of v plus the magnitude of w. That does not work. They generally are not equal to each other. The only way that they're equal to each other is if the two vectors are pointing in the same direction. Very uncommon that that takes place, but not impossible.